Dear sir, I'm Ankit Patnaik, a team member of Team RF Fixer. So I would like to present you an overview of the off converter model designed within the GNU radio framework. So this model is proficient in transforming a lower band frequency into a higher band frequency that you give in the problem statement. So in this prototype, I have incorporated two signal sources, each operating at 200 kilohertz, and also I have taken the sample rate value that is 1 megahertz. So I have taken the sample rate 1 megahertz and two frequency, a frequency range 200 kilohertz, and also I have added a noise source that is a Gaussian noise source of amplitude 1. So the reason behind adding a noise source is that it is a preferred choice in signal processing due to its effectiveness in simulating random variations and errors encountered in real world data. So by adding a controlled element of randomness, we can replicate how signals may be influenced by factors such as interference and measurement of inaccuracies. So now we have given all the signal sources and noise sources as an input to the multiplier block, and the output of the multiplier block is given to a block that is called throttle. So basically in the throttle block, it utilized to regulate the data flow throughout a signal processing flow graph. So it serves the critical function of limiting the data transfer rate between individual blocks, so thereby preventing data overload and ensuring that the processing adheres a predetermined data rate. So this is instrumental in maintaining a stable and effective data flow in a software defined radio application. Okay, so subsequently the output of the throttle is now given to a band pass filter. You can see over here we have designed a band pass filter with a low cutoff frequency of 399.99 kilohertz and a high cutoff frequency of 400.01 kilohertz with a sample rate of 1 megahertz and a gain of 1. So the following filtration process, the output is now directed to a GUI frequency sync. Here you can see the GUI frequency sync of FFT size 1024 and the bandwidth is here also 1 megahertz. So and you can also see that here I have added another GUI frequency sync which is directly connected to the throttle so that we can see two different frequency which is achieved after bandpass filter and which is achieved after the throttle, like after multiplying all the signal sources. So after executing this model, you can see the output over here. So these two are the signal, one is before filtration and another is signal after filtration. So in this graph you can see that when the two signals are multiplied and when the signal is added with a Gaussian noise, you can see the variation of the signal, or you can see the frequency response of the signal, whereas when we given that multiplied signal or that noisy signal to the filter, to the bandpass filter, you can see the output. This is we have given two signals of frequency 200 kilohertz and we have to convert that signal to 400 kilohertz, and this is the output, the exactly 400, that peak value over here. You can see that like this. Yeah. So we got for 0.400 megahertz, or you can say 400 kilohertz after the filtration. So this is the model of the down conversion. It exactly same as the up conversion model. just I did some minute changes in the bandpass filter, and I have taken one signal source that is of frequency 400 kilohertz, and I have given another signal source of frequency 200 kilohertz, and with a noise source I have given all the output of these sources to the multiplier, and the bandpass filter. Here I have given the low cutoff frequency, that is 99.99 kilohertz, and the high cutoff frequency, that is 200.01 kilohertz, so that I can get the desired frequency, that is 200 kilohertz frequency. So this is the output of the down conversion model, and here you can see the noisy output when we have added the noise signal or the noise sources to the signal, and here you can see the output, that is 200 kilohertz, or you can say that is 0.200 megahertz. So these are my initial prototype where I took some small ranges of frequency, and after that I will work upon the L band and C band and K band, and I will try to convert in the similar way to convert the L band to C band, that is convert the 1 to 2 gigahertz frequency band to 4 to 8 gigahertz, or you can say 14 to 18 gigahertz frequency range.
Currently I am working on the hardware implementation part, and also my whole team is working on the model in GNU Radio. So I will give you a bit introduction about this model. So this is a model that is NI-USRP2901 by National Instruments. It can support up to 70 megahertz to 6 gigahertz, so we can easily implement our model which can convert L band to C band and C band to L band. We can see in this hardware there is two port for transmitting and receiving, and two port for receiving, and here you can see that the transmitting output is maximum 20 decibel, and input is maximum 15 decibel, and it can support the all RF ports up to 50 ohm, and in the back you can see this is where I have connected my SDR to my laptop, and this is the whole design. This is the design that I am currently doing, the frequency multiplier to convert the frequency from high range to lower range. And here you can see that this is the power port. It can support 6 volt DC and 1 ampere current maximum. So this is where we will connect the two ports for inputs or outputs, and this is the USB port. Yeah, this is the whole hardware model that we are currently doing, and I promise we definitely complete this project